It's my pleasure to introduce talk. The speaker is Alina Vdovina from City College of New York and SUNY. Higher structures in mathematics, buildings, K-graphs, and C-star algebras.
Yeah, thank you very much for the introduction and for the invitation. And yeah, of course, I would much prefer to be in Paris now, but it's really hard. It was hard to come in person, and so like this talk, Anna, thank you very much, Anna, for your kind invitation. And my promise was to talk about the higher dimensional analogs of Thomson's groups and Grigorchuk groups. But then I realized that I did like in order to even start talking about those higher dimensional generalizations, you have to first introduce the analog of trees, right? Because we know that also today we had two very nice talks, and also the first talk we had the picture of trees and their automorphisms. But what happens that if we think about any kinds of generalizations in higher dimensions, then it turns out that instead of trees, we have to look at buildings and building-like complexes. And since it's a kind of remote talk, I decided to talk about them, this kind of higher structures, which I was involved in creating recently, and their connections to other fields of mathematics, because it turns out that we get a lot of very interesting insights from the theory of sister algebras and even from theoretical physics. But I will try to be like as brief as possible, and then probably you will ask questions in the end, and kind of to I would like to generate some kind of discussion. So first of all, this is my plan. I would like to briefly just to give them flavor what are the buildings. I'm sure this audience probably knows it, but just the way how I look at the buildings as universal covers of some complexes. And then I will talk with some connections with Drinfeld-Manin solutions of Yang-Baxter equations, which I was really quite pleased, and it was a bit of unexpected connection. And then I will talk a little bit of so-called like K-rank graphs and therefore Neumann algebras. But then I will like at least just to show briefly that actually it's all connected to arithmetic buildings. Okay, so first of all, like probably you all know that first series of buildings were introduced by Jacques Tietz in 50s, and of course, like I'm sure that everybody in this audience knows about Jacques Tietz, who was for many years in Collège de France. And so buildings have algebraic, analytic, number theoretical, various kinds of aspects, and they consist of chambers and apartments satisfying certain axioms, where each apartment consists of a set of chambers. And we give some examples instead of a formal definition. And so we know the password for this meeting, which is a valence of a graph with of a free group with 107 generators, but this is much easier picture. This is a Kelly graph of a free group with just 2 generators, and of course we know all this picture, but so I will not talk too long about it. But why do I need it? Because I want to see about the Kelly graph of a free group is a one-dimensional building, so we can think about the edges of the graph as chambers and apartments as paths from one point at infinity to another point in infinity. And of course, we can check those kind of standard axioms of a building that any two chambers are contained in the same apartment. So of course, if you take any two edges in the Kelly graph, you can always find an infinite path from one point in infinity to another, which contains both of them. And also another motivation why I start with this picture, because of course in the dimension 1, it's completely clear that the Kelly graph of the free group is a universal cover of a wedge of two circles. And actually to think about this Kelly graph of the free group of two generators, we don't need have this reference to the to this kind of finite graph. But when we will start to discuss higher dimensions, it will be relevant that we will look at some kind of finite complexes such that their universal covers are buildings. So that's why it's good to keep this picture in mind, because I will say what is the analog of the wedge of circle, what is the analog of a free group, and what is the analog of the Kelly graph of the free group. Okay, so think even when we go to the dimension 2 and we think about the apartments of what are the apartments for our buildings, then they are already kind of planes tessellated by certain polygons. And for example, if we talk about hyperbolic buildings, we talk about kind of regular tessellations of hyperbolic planes. And if you talk about Euclidean buildings, it's either A2 tilde tessellations of, so what is the A2 tilde tessellation? It's a tessellation by regular triangles. But in this talk today, I'm going to talk like quite a lot about products of trees. And of course, just as products of trees, it's not difficult to construct any groups acting on them. But what is interesting about the products of trees, when we start to look at groups which are like arithmetic and which are kind of irreducible. But for the moment, I just remind this definition of a polyhedron which I use, that again, like this definition now is for dimension 2, but it's easily can be generalized for dimensions 3 and higher. So we say that generalized polyhedron is a two-dimensional complex which is obtained from several decorated polygons by identification of sides with the same labels respecting orientation. So it's kind of easy exercise. If you take those 4 polygons and you identify edges with the same letters respecting orientation, then the universal cover is going to be a product of 2 trees, and the fundamental group of the complex will act simply transitively on this product of trees. And of course, as a group itself, this kind of, it was known for a long time that if you glue together those 4 squares, then the universal cover is a product of 2 trees. But what was kind of original contribution about 5 years ago with Jakob Stix, that we proved that in addition, this group has a arithmetic structure, that it's a arithmetic subgroup of PGL2 cross PGL2 in finite characteristic. And this kind of brings many interesting properties of this group. And just again, like I always give those definitions in my talks, because there are always some new people in the audience. Just a reminder, what is the link? If we take a sphere with a very small radius at a point of the polyhedron, then the intersection of the sphere with the polyhedron is a graph, which is called the link at this point. So for example, like here, if we take this point of a polyhedron, then the link is just a graph with 5 vertices and 4 edges. And examples like links of manifolds are spheres, but we need highly singular spaces as links to construct buildings. And if in the example I showed with 4 squares, as I already mentioned, we would get a polyhedron with 1 vertex, but the link at this vertex is a graph with 8 vertices and 16 edges. It's a like complete bipartite graph, but we can also think about the complete bipartite graph as the graph of a diameter 2 and girth 4. So the diameter is the maximal distance between 2 vertices, and girth is the length of the shortest cycle. And of course, the distance, it means the number of edges which you need to pass to go from one to another. And so first of all, I would like to connect polyhedra in buildings. So the result below deals with the 2-dimensional case, but I generalize it to arbitrary dimensions as well. It's just kind of easier for a talk, especially a remote talk. So there is this, again, it's a reformulation from Ballman and Brin because they use completely different terminology. But nevertheless, if we look at the compact 2-dimensional polyhedron, and if all links are graphs of diameter m and girth 2m, then the universal cover of the polyhedron is a 2-dimensional building. And what was kind of my contribution in early 2000s that I kind of showed explicit constructions of polyhedra with given links, because the result of Ballman and Brin is kind of very general, and even so there were some isolated examples, but I kind of made the construction of this polyhedra into kind of theory. But actually the life becomes really complicated when you go to dimensions 3 and higher, and again, like relatively recent constructions with Runok-Perron and Sticks involves quaternion algebras in finite characteristics. And there the buildings have like chambers which are n-dimensional cubes, and apartments are Euclidean spaces tessellated by those chambers. But again, I would like to give kind of a light talk, so I will not give general constructions of our results with Stick and Raghunathan-Perron, because it would need introducing the theory of quaternion algebras. And if you are interested in quaternion algebras, there is a book of joint work which called quaternion algebras. It's really quite a non-trivial theory, but I would like just to give a flavor. How do we get those kind of quaternion groups? So, but okay, since I gave like the first set of definitions, probably there are some questions now. Probably I should like pause for a couple of minutes because I introduced the main definitions of like buildings, links, polyhedra. So probably now it's a good time to stop and ask for questions. So I will check the chat. So, okay, any questions?
No.
Okay, so good. Then I will just continue with kind of explicit examples of quaternion groups acting on buildings, and such examples were known by Burger and Moses in dimension 2. So in a way, if you, in this example here, if you restrict yourself only saying A's, like A1, A2, A3, A4, and B1, B2, B3, B4, B5. So this example itself appeared in works of like Burger and Moses and of Diego Ratagui, who was a former student of Burger Moses. It was like more than 20 years ago, but then there was kind of a interesting question: can you do this in higher dimensions? And in higher dimensions, like really you get some extra compatibility conditions, which, as I said, that could be solved only by using like very non-trivial number theory. But again, like here you have an answer. So you see you have like Hamiltonian quaternions like IJK. And what happens that if you are lucky, and I said not just lucky, using certain non-trivial theory, you can get such like A1, A2, A3, and 4, and then they turn out to have such a nice structure. Then when you multiply those quaternions, again in certain combinations, then you get a nice group, right? So actually those A1, A2, B2, B3, so the relations in this group, which I call here like 3, 5, 7, the relations come from multiplication of quaternions. And indeed, like it's a like easy exercise, you can see that, okay, when you already know those quaternionic expressions, then you get the relations of this group. But then when you already have those relations, you can be quite happy, because we can use for this group, we can use our construction, which we had before. So actually, when we, for each a relation of length 4, we can get a square, and then we can use our construction, which we had in the beginning. We can identify letters with the same labels respecting orientation. But what will be different here, then we will have to add the cubes when we can. So because here we will have a lot of this will be like a cut zero cube complex, and in a way, so we have the fundamental group of this cube complex is going to be like an arithmetic group, and it's going to be kind of just infinite, and so on. A lot of kind of interesting properties. And then later on, of course, like in this talk, I will not give the details, but then later groups like this coming from quaternions can be used to construct non-residually finite groups acting on cubed complexes of arbitrary dimension. So this was also like our contribution of sticks to get, like, I believe that it was first very explicit examples of non-residually finite groups acting on cube complexes of dimension like 3 and higher. But as I promised today, I wanted to talk about relations of the kind of geometric group theory and arithmetic geometry with like more analytic subjects. So first of all, let me define the Yang-Baxter equation. And yeah, so then let X be a non-empty set, and R from X squared to X squared be a bijection given with the following formula. And we call R a set theoretic solution of the Yang-Baxter equation, or Drinfeld-Manin solution, because actually in the literature, people call by set theoretic solution something which is much more restrictive. And I was even like asking Manin explicitly, like if those restrictions are coming from some kind of intrinsic interpretation from physics, and he said that no, not necessarily. So actually this kind of more general, that's why I called it like Drinfeld-Manin solution, because it's somehow motivated by very early papers of Drinfeld and Manin. And this is the solution. So actually, what is this Ij means acting on the i's and j's components of X3, right? So this is a kind of a direct. So here we have a Cartesian product of X with itself, but here it's like triple Cartesian product of X with itself. And it's surprisingly, this kind of Yang-Baxter equation really appears in many fields of mathematics and theoretical physics. But then, like using cube complexes and like our constructions with sticks, it turns out that one can get new series of solutions and a new geometric invariance to ensure that these solutions are really new. So it's like my paper about a couple of years ago. And so just a very quick reminder that the classical Yang-Baxter solution, it involves a linear operator from tensor products, where V is a vector space and has the same form. And how, like from those Drinfeld-Manin solutions, which we can get from cube complexes, how we can get those classical ones, that we just take a vector space, which is spanned by the set X on the previous slide, and this gives you solutions of the classical Yang-Baxter equation. So of course you can, if you're not interested in this kind of theoretical physics connections, you can just ignore the slide completely. But this is like for people who are, this is kind of a relation to this kind of classical linear operators. But now let me give the connection of Drinfeld-Manin solutions and groups acting on products of trees. And again, I will take only this example 357, which consists of 24 cubes. And this is one of the cubes. And then I will just say how we form the set X. So the set X is taken to be the set of labels on the edges of the cubes. And the bijection R is induced by squares of the complex. So just in general, if you haven't seen the Yang-Baxter equations before, it's usually quite difficult to construct this R, and it's so-called like R matrices. There is the whole theory, but how to do this. But it turns out that indeed there is this kind of connection with cube complexes. And how we construct this R matrix or bijection, if we have a square, if you have a square in our complex xi, xj, xk is L, then we define of xi, xj, x as xl inverse, xk inverse. And for example, in the if you have this 357 example, the set X has 18 elements, but the R matrix has size 324 through 324. So this was kind of new that you can really get such huge solutions just quite quickly. And I can see okay, so this is how we get cubes, right? The cubes we get from quaternions, then we glue together those faces. And what is kind of interesting that, of course, if you have all those 24 cubes and we glue them together, then the universal cover is a product of three trees. And just to give you the flavor, how this Yang-Baxter equation, why indeed from the cubes we get solutions of the Yang-Baxter equations, we let's apply this Yang-Baxter operator, one side of the Yang-Baxter operator to A1, B1, C2. So like again, in our complexes, you can always, every triple you can put on the diagonal over cube, right? Such a kind of path from one point to the diagonal point. So we have this path A1, B1, C2, and then we apply this Yang-Baxter operator to it by the rule which I defined on the previous slide, and we get a C4 a B2 inverse A1 inverse. But then if we get the other side of the operator again, we apply it to the same path, we also get C4 B2 inverse A1 inverse. And what is interesting that the group, the fundamental group I was talking before, it can be interpreted as a new invariant for the Young-Baxter equations, and it's also different from so-called structure group used in the algebraic community, and it turns out to be much more kind of efficient invariant because it really distinguishes different solutions. Yeah, and as I already mentioned before, that this kind of shows that indeed the solutions coming from cube complexes didn't appear before. And now I would like to just highlight another bridge with sister algebras and von Neumann algebras via so-called K-graphs. And in our new work with Nadia Larsen, we have like a quite combinatorial interpretation of these K-rank graphs. But again, for a shorter talk, the categorical definition is much better because it's shorter. But again, if you are not too happy with the category theory, then I suggest that you can ask me question or like look at our preprinted archive with Nadia Larsen, where we kind of introduce the notion of like k-dimensional graphs without category theory. Okay, but nevertheless, like a countable category C is said to be a higher rank graph or K graph if there is a functor from the category to the natural numbers to the power K called the degree map, satisfying the unique factorization property that if D of A is n plus n, then there are unique elements A1 and B2 in the category such that A is a product of A and B, where the degree of A1 is m and the degree of A2 is n. And so indeed, here you have like morphisms and so on. It's really kind of quite tricky category theory, but it turns out that there is a very nice connection with cube complexes. And usually it's quite difficult to work with those degree maps, but it turns out that you can find in the interpretation by looking at pieces of apartments. So in a way, if you have an Euclidean building, you can look at the rectangular pieces of apartments, and they can tell you what happens with your degree maps. But now I would like just to state some of our joint results with Nadia Larsen that we gave like a lot of new constructions of those K-rank graphs. And moreover, then we even, it was really surprising for me that the main construction was again like using cube complexes and setting like very explicit connection between cube complexes and higher rank graphs. But then, which was kind of new in our work with Nadia, we started to look at the spectra of those higher rank graphs, and they turned out to be related to the spectra of Ramanujan complexes, which appear again in our older work with Jakob Stix and Niti Raghunapirom. And then, because usually like in the theory of von Neumann algebras, people always look at, it's almost like coincidence which lambdas you would get with your 3 lambda factors. But we have found some kind of completely uniform way to get those three lambda factors. Again, I don't define them or whatever, because I just wanted to establish the connection for the specialist. But for this kind of spectral theory of K-rank graphs was possible because I had this earlier work with Stix and Ragunapirom about Ramanujan graphs and Ramanujan complexes. And I was talking about it at the same seminar in Paris 3 years ago. But since, of course, no one was, not everyone from the audience was present there. But on the other hand, during those 3 years, it turns out that it has many more connections to other fields. So I would just kind of quickly remind this kind of our construction of Ramanujan complexes. And of course, like usually you start with the Ramanujan graphs. There is this kind of very famous construction of Margulis and Lubotsky-Philip-Sarnak about 88, where they really gave the first explicit examples of Ramanujan graphs. And what does it mean, the Ramanujan graphs? It means that the all non-trivial eigenvalues of the adjacency operator have absolute value lambda, which is greater, less or equal than 2 square root of q, right? It's for regular graphs, q plus 1 regular graphs, and the estimate it's lambda is less or equal than 2 square root of q. But again, the original motivation was coming from Alona bound, which tells you the limit, in the limit, the non-trivial eigenvalues are greater or equal than 2 square root of q. So that's why this kind of bound 2 square root of q is the best possible bound. And so what happens for the higher dimensions, that you can define adjacency operators in the direction v. So imagine you have this kind of cube complex of higher dimensions, and you can interpret that you have like edges of different colors, and each color comes from one dimension. And then you can define the adjacency operator, but actually it's not just one adjacency operator, it's like many adjacency operators. But if you have a kind of nice cube complex, it turns out that all those adjacency operators commute. So it makes sense to look at the simultaneous spectrum, and we just, by analog with the graph, we define cubical Ramanujan complex. And those cubical Ramanujan complexes, they are different from what usually Lubotsky and his collaborators look at. And of course, they have also very nice constructions and so on. But then it turns out that those cubical ones, they have quite good potential for applications. And of course, like, I would never think that I would have some like applications for theoretical computer science, but recently I had like a paper with 2 other mathematicians and 3 computer scientists, where this kind of where it was important that it's really this kind of arithmetic which comes from our original papers with Stix, like and Ragunapirom from here. This was really kind of important, but you can ask me later. And here I just wanted to remind what are the Ramanujan cubical complexes, and say that they appear as quotients of products of trees, but by those quaternionic groups in finite characteristic. And again, it gives like larger sources of high dimensional expanders and so on. But those quaternionic groups, they are even slightly more tricky than the example I showed in the beginning on my talk, because you have to look at the quaternion algebras, which are in finite characteristic, and they are more difficult to define than the classical Hamiltonian quaternions. But again, it's all already published and so on. And the finite characteristic allows you to find this kind of very explicit estimates for the eigenvalues. So, for example, like the old examples of Burger-Moses wouldn't have those kind of nice eigenvalues, because you have to use this kind of non-trivial theory in finite characteristic. Okay, and just the pictures define the proofs that you have to move all those squares together and glue them and analyze the structure of the words which are written on your cubes. And just I would like to finish with the further directions of research. And so my talk was kind of more invitation to discuss and just to say that it's interesting to look at those kind of higher structures. Thank you very much for your attention.
Thank you very much for your talk. I don't know if I'm disconnected.
No, I can hear you very well.
Yes, that's great. So thank you very much for your talk. So just a small question. I understood you decided maybe not to speak today about some high dimensional Thompson groups or something, but did you mention that maybe we may ask you something at the end? Just
Yeah. So this was kind of indeed I wanted to, because I realized that to talk about like high dimensional Thompson group, it's you need probably like a little bit longer, because it's really, but I can give the idea, right? What you how you get the high dimensional Thompson groups with relation to what I was talking now, that I was talking about buildings as like glued from cubes. Yeah, and let's even start with the dimension 1 when we talk about trees, right? How you can think about one dimensional Thompson group. You can think about free semigroup acting on a tree, on a rooted tree, and right, you can think that you have like infinite tree and you have a free semigroup acting on it. And for example, we say that S is a free semigroup, which is defined by A and B. But then also, like, we can define the boundary of this tree as semi-infinite words, and we can think about the semi-direct product of kind of continuous functions of on the boundary with the semi-group action. And this is so-called like Kunz's sister algebra. And what is interesting, that this kind of analytic interpretation of the Kunz algebra also induces interpretation of a Thompson group. So how we can think, so again, like we talk about the boundary of this tree which can be interpreted as kind of Kelly graph of a semigroup. And then we can think about partial isometries of the boundary. And the Thompson group can be presented as the group of partial isometries of the boundary of this tree. And in the same way, the higher dimensional Thompson groups can be presented as the partial isometries of boundaries of a building, right? So, but I can again like answer further questions. So probably like you can ask if this kind of interpretation in dimension 1 is clear, because it's very unusual interpretation. So that you can
maybe can you comment please? Indeed, you mentioned that even in dimension 1 something is not so clear. Or...
No, it's clear. It's just probably not so well known that you present the Thompson group V, right? Actually, it's about, I'm talking about Thompson group V. I present it as the group of partial isometries of the rooted tree, of the binary rooted tree. And how it goes, that we look at, of course, it's like the boundary is infinite, but what are the good news? That we can apply finite technique. We can look at pairs of carrots, right? We can look at pairs of carrots of finite trees. And of course, this interpretation is very well known, right? That we can present the elements of Thompson group as pairs of finite binary trees with the same number of leaves, right? But now, how we think about just one carrot, we think about it as all infinite words starting with those prefixes of a finite tree, right? So in a way, we go from a finite tree to a set on the boundary. So if we, again, like, let's take one carrot, and we can look at all words so then all words in A and B can be there is a disjoint union of all words in A and B, which start either from A or from BA or from BB. And we can think about it as the partition of the boundary of this rooted tree into disjoint pieces. And so we call it like, it's called like prefix code. And so if we talk about so there is this kind of language of interpretation of the Thompson group, V in prefix codes. And what happens that Thompson group V can be also interpreted as like piecewise continuous homeomorphisms of the interval. But when we go to higher dimensions, this somehow breaks down. So we have to keep kind of this combinatorics. And what happens that in higher dimensions, we talk about the pieces of apartments, and we talk about kind of analogs of those pairs of carrots, but instead of carrots, we have pieces of apartments, but then they correspond to partitions of the boundary of a building into disjoint pieces, and the group can be interpreted as the kind of group of partial isometries of a boundary of a building. But then why I was bringing into the game those sister algebras? Because such kind of Thompson-like groups are usually very difficult to distinguish. But this kind of connection with sister algebras, you can use certain methods from the sister algebra, which I was also kind of doing with my students. And one can compute so-called K-theory, which are kind of abelian groups, and they distinguish your high-dimensional Thompson groups. But so what happens that all this technique I was explaining today, it's kind of building up towards this kind of high-dimensional analogs of Thompson groups and Grigor 2 groups.
Thank you. May I ask you something in dimension 1 before going to high dimension?
Yeah.
I'm not sure I followed everything you said.
Okay. Yeah.
If you have some group acting on a counter set, like the group of Nekrashevich, does your correspondence work? Or?
Yeah. Very good. It's actually, so here, it's a very, very good question. So what is this boundary of the streets, indeed this counter set in the work of Nekrashevich? Yeah. So just I gave you the easiest possible example, but what is the problem that when you go to higher dimensions, your boundary is not necessarily counter set. And this was probably why those like higher dimensional generalizations, it took them some time to appear. But of course, there are some where you have counter sets as well, but there are some where they are not. For example, like in certain type of buildings. Okay, I didn't write it up yet, and because I want to have like next works very, very general. But for example, like for like groups acting on hyperbolic buildings, you can also have this kind of Thompson/Grigorchuk-like constructions, or like we can say that it's kind of higher dimensional generalizations of Nekrashevich groups, because Nekrashevich groups are some kind of blend of Thompson groups and Grigorchuk groups. And then like one can think about higher dimensions, but indeed you don't have a counter set anymore. So you have to think in different terms with this kind of, with Mark Lawson, we call them prefix codes. And but here the counter set is the boundary of the binary tree.
Thank you. And just may I ask you, for group of Nekrashevich or for the group of Grigorchuk, is there any chance to have some high dimensional analog of intermediate growth, or what happens with growth for possible?
Okay, this is kind of very, very interesting question, because with this abstract interpretation, it's even difficult to write generators in relations. And even with the first kind of generalizations of Thompson groups, just I will like. So with them, for the Thompson groups, it's not even so easy to find the generators on relations. And now we have ongoing work with Britta Nussingens and Conchita Perez on even proving that many of those high-dimensional Thompson groups are F-infinity. So this comes together also very good with one of the talks today. That
in particular, you will have finally presented examples, right? And then for some then high dimensional analogs, maybe of Nekrashevich group, of Grigorchuk group, your groups you said you don't know generators in
no for the so what I would like to say that for in the case of this far-reaching generalizations of Thompson groups, it's already everything is written. Everything is like published, right? We have a paper like in Advances with Mark Lawson, and then it's that it's F-infinity. Okay, it's not yet written, but it's not yet finished, but it's mainly written. But about saying Grigorchuk groups and Nekrashevich groups, it's little bit further. It's not somehow kind of this kind of working ideas. It's ideas which I'm sure it works, but it's not written because one of the ingredients today I was talking about this higher rank graphs, and a lot of work on this generalization of Thompson groups with like Lawson and then also Lawson and Sims. It's this kind of higher rank graphs. It's a very important ingredient. So that's why I said that there are a lot of ingredients which you need for this work. But then for Grigorchuk group and for Nekrashevich groups, one needs like even this first building block. It's like with Lawson, we called it a generalized higher rank graphs, and we have only like the first paper where we make the construction of those higher dimensional graphs, generalized K-rank graphs. So in a way, in this kind of project, it's of course it's much slower than to work with one group, but then when you succeed, it turns out that all kind of groups of the kind coming as particular cases. So actually, it's kind of so saying it was Thompson groups, like for example, all those Brin groups, they come as as a particular case of our construction with Lawson and so on. But there are many more. Yeah. So, but growth, it's the next question. I think it's much more subtle question. But what would be and I think probably what we should discuss further, to check if there are some invariants in this kind of intrinsic structures which tell you what the growth is going to be. Because it may happen that the growth is already kind of hidden in this kind of, there is the skeleton which you use to build up either Thompson groups or Grigorchuk groups, and probably there is something which you can catch there which tells you this would be a dream, right? Because I'm quite hopeful, because this dream to find some invariants coming from somewhere else, they already kind of came through, right? I was quite happy when it turns out that this kind of K-theory of sister algebras became useful to distinguish the groups, right? Because to distinguish the groups of this kind, like this kind of higher dimensional Thompson groups are quite hard, because it's very hard to find generators and relations, right? That it's indeed, I said that we have this ongoing work where even we don't cover all our construction. But what is interesting, that you can associate with this higher dimensional Thompson group, you can associate a sister algebra. And then if you manage to compute its K-theory, and K-series are billion groups, you can think about K-theory, it's kind of far-reaching generalizations of homologies. And then suddenly those groups are different. And then it turns out that the groups are different as well. So yeah, and actually, one of the examples that indeed you can, if you come back to the example of the Kelly graph, in the beginning of my talk of the free group, that you can, with this picture, you can associate Thompson-like group, but it's not going to be a group V, right? Because you can fix the vertex, and you can think about the boundary of this tree, right? And you can think about like a tree. First, you have 4 edges, but then you have like 3 edges coming each time. And using this kind of approach with carrots, right? You can look at the finite subtrees with the same number of leaves, and you can look at their pairs. And then you have another group which looks like a Thompson-like group. And then the question, how do you distinguish it from the Thompson group V? But then, like there is for the group which come, for the Thompson-like group which come from this tree, you get so-called like sister algebra, and its K-theory turns out to be Z cross Z. So the invariant coming from this picture is Z cross Z, and the invariant for the Thompson group V is trivial. So the case theory of this Kuntz algebra is trivial. So straight away, I can show like two examples of Thompson-like groups, which probably not that easy to distinguish, but we can distinguish them straight away using the case theory, because it's like for this one, this invariant is trivial, and for this one is Z cross Z.
So thank you. I have some other questions, but I guess I will ask them later.
Okay,
can I ask you a
probably
question?
There are some
get
other
together,
questions from the participants.
Can I ask you a question?
Yeah, sure, Leonid, it would be great.
So Alina, you mentioned this group which is not residually finite. Is it easy to see that it's not hyperbolic?
Yeah, it's a great question. Yes, it's very, unfortunately, it's very easy to see that it's not hyperbolic.
So how to see it?
Because it's it acts on a product of trees.
I see.
It can be like horrible
non-trivially.
trees. And what I would like to say that it's not, because also another question which I get quite often in the geometric group theory community, they ask how do I know that it's not like special or extra special. So
Right.
this is easy to answer because it's it comes from this arithmetic group, and it's so-called like irreducible lattice acting on a product of trees. It's even like it cannot be even virtually as a product or whatever. So, and it's also like just infinite, right? So it's yeah, this is easy to see. And the next question is just I think it's also possible, just one would need a little bit of computer search, and for the moment I don't have a good student who not a good student, but now I don't have a student at all because I just moved, right? But this would need a little bit of computer search to go from our non-residually finite examples to simple examples, because Burger-Moses also like there are simple groups, but actually very in a way, yeah, it's slightly different technique, but when you go to the higher dimensions, yeah, it's okay. I have some candidates, but as I said, that one would need a little bit of computer search to show that they are simple as well.
Mm-hmm.
Any other questions or comments? Actually, we have a small technical problem. I know your talk is transmitted in room W, and I know that the people are really hearing you, but it seems that we have maybe some difficulty to ask the question from there. Just in case somebody hears us and could not ask a question to Alina right now, I guess. Everybody can ask them maybe by
or
email.
write in the chat,
But
right?
it's great to see Alina again. So Alina, thank you. It's really so many really challenging problems from all areas of geometric group theory, very different one and absolutely challenging. So it seems like to be a very interesting project. So if there are no comments, those who are with us, maybe let us thank Alina again. And
yeah, and Grace, thank you very much. It was more invitation to discuss, right, than like too many details. Yeah. I cannot hear you anymore.